Hello everyone, good afternoon. I'm Ashish Kumar Das. I am doing PhD at University of Idaho. My presentation is on ammonia recovery from anaerobically digested dairy manure by using electrodialysis coupled with membrane technology. So here, oh, Oh, okay. Thank you. Here, at first, there is some knowledge about what is the condition of ammonia nitrogen before anaerobic digestion and after anaerobic digestion. So during anaerobic digestion process, that organic nitrogen that converted to ammonia nitrogen, especially during deamination process, and it creates ammonia and ammonium. And we found in our lab analysis that before anaerobic digestion process, that ammonia concentration almost 550 milligram per liter, and after anaerobic digestion process, it increased 3 times, almost 1500. So there is we concerned about to recover that ammonia. If we don't recover it, and if it remain in that dairy wastewater and it get mixed with surface water bodies, that can create some environmental issue like eutrophication, algal blooming. That's like problem. So we need to do it. So what really happened when we applied dairy manure into the cropping land? So it's not totally utilized because some nitrogen that mixed with surface water bodies by surface runoff or leaching. So we should definitely concerned about it regarding environmental hazardous effect. And that most common ammonia production technology that is called Haber-Bosch technology, and it is not so environmental friendly technology. Sorry, about 3 to 5% natural gas consumed in this technology, but main drawbacks is it creates almost 2% carbon dioxide gas. This is an important greenhouse gas. So we should we should identify some sustainable technology that has no detrimental effect on environment. So in dairy operation, if we classify dairy operation in different times, in previous time, at first, dairy wastewater was directly applied to agricultural field. And from there, ammonia and other gases that emitted into the environment and that create environmental pollution. And after that, anaerobic digestion process added to that dairy operation system that can create biogas that meet up that energy demand of dairy farms. And nowadays, dairy operations are more sophisticated, and it's mainly separate solid and liquid part. And that solid part used as bedding and soil amendment type things, and liquid part, there are still some nutrient, nitrogen and phosphorus. And this nitrogen and phosphorus can be recovered as a value-added product like struvite, calcium phosphate, and ammonium sulfate. So there need to develop some technology that can be good to recover that nutrient. And for this sense, we developed our research to a sustainable electrochemical nitrogen recovery technology. And in this research, I mainly applied different level of current density and show their effect on recovering ammonia nitrogen from liquid dairy manure. So this is my experimental design. I mainly used an enclosed 3-chamber system where anode and cathode chamber are separated by a cation exchange membrane, and cathode and trap chamber separated by a hydrophobic gas permeable membrane. And as an anode, I used lead oxide coated titanium, and as a cathode, I used stainless steel. And to recover ammonia nitrogen in trap chamber, I used 1 molar sulfuric acid solution. So when I applied current, they create 2 types of reaction. In anode, they create a reaction that called anodic electrolysis, and that time they produce some proton and oxygen gas. And in cathode, they create some hydrogen reduction reaction. They create some hydrogen and hydroxide ion. That hydroxide ion mainly increase the pH of catholyte, and that help to convert ammonium ion to gaseous form of ammonia. And that gaseous ammonia pass through the gas permeable membrane and mixed with sulfuric acid solution and create ammonium sulfate that can be used as a liquid fertilizer. So here is the form of ammonia and their behavior at different pH level. So below 9 pH, ammonia behave like ammonium in form. And with increasing pH, ammonia form in a volatile form, that ammonia gas form. So we mainly apply this principle to recover ammonia from liquid dairy manure. So here, the scenario of different current density we applied, and so their effect to change the pH of anolyte and catholyte. We can see that I applied zero current density. That means no current I applied, and there is no change of pH of anolyte and catholyte. But with increasing current density, I can see that rapidly change of pH of both anolyte and catholyte. And for 150 ampere per square meter current density, that pH of anolyte reached from 8.5 to nearest 2, and for catholyte it was reached almost 13. And that rapid change of pH mainly worked on to change the formation of ammonia to ammonia nitrogen gas in catholyte in cathode chamber, and that helped to pass through that gas permeable membrane, and it's absorbed in sulfuric acid solution. Here, that change of anolyte in different current density from, if we compare current density from 50 to 150 ampere per square meter, that almost 12-fold increasing of acidic environment in anolyte. But in case of catholyte, it's shown almost 170 times greater in change of alkaline environment in catholyte solution. So that's the result of ammonia removal by this different current density. We can see that maximum 100% removal happened for 8 hours treatment time for 150 ampere per square meter current density. There is still some removal for zero current density, because there happen due to change of concentration gradient of the anolyte and catholyte. That's why there's still very small amount of removal happened over there. And in recovery scenario, we got 75% recovery. And for that same condition happened for concentration gradient variation, there have some little bit recovered for no current density application. But with increasing current density, there mainly happen Faraday's law of electrolysis that accelerate the process to convert ammonium to ammonia, and that pass through the gas permeable membrane and recovered in sulfuric acid solution. And here is the distribution coefficient in different chamber at different time. We can see that when we start our treatment, that ammonia concentration in anode chamber was maximum. And after the treatment, that ammonia position changed to the trap chamber. And in anode chamber, that ammonia concentration is very low. That means it's recommend very good recovery condition. And I must say that with increasing trap chamber with cathode chamber, that help to to prevent the back diffusion, that go back that ammonium ion through the cation exchange membrane to the anode chamber, that help to back diffusion things by adding recovery chamber with cathode chamber, and it enhance that recovery efficiency of ammonia nitrogen. This is the mass of ammonia recovered in trap chamber. We can see with increasing current density that mass of ammonia in recovered chamber in sulfuric acid solution that also increased. It ensured the quality of recovered product of ammonium sulfate, that valuated product we have our ultimate goal to recover. So this ensured that economic perspective, that quality of the recovered product. Next, here is the nitrogen flux that flows through the cation exchange membrane and gas permeable membrane. So we can see with increasing current density that nitrogen flux also increased, and maximum nitrogen flux for 150 amperes per square meter current density, it was 616 gram nitrogen per meter square per day. And for gas permeable membrane, the nitrogen flux was near to 300 gram nitrogen per meter square per day. And for that maximum nitrogen flux around 600, our current density 45 kilowatt per kg per nitrogen. So I compared with my result with some other previous studies. They use different types of waste water. Here I got good result, I would say. There is a still scope to research to decrease that energy consumption. I must work in future to reduce that energy consumption, because there is still scope to reduce the energy consumption. So I must say this recovery technology mainly bases on orthogenic acid and base production by using electrolysis technology. So we don't need to change the pH of anolyte and catholyte by adding any alkaline solution or acidic solution. This only changes by applying electricity. So by using this technology, I have planned to recover nitrogen and phosphorus simultaneously by this enclosed electrochemical system. So that's my future plan. And this work is funded by Idaho Sustainable Agriculture Initiative for Dairy Project. That's USDA NIFA federal government funding project. That's it. Thank you very much. Thank you.